Okay, so here's what we were talking about last time. We were talking about the non-diagonalizable case. Remember, the diagonalizable case worked out just super. The conjugation trick that we're trying to pull again here, in the diagonalizable case, resulted in what we might call a diagonal system, which we then, upon writing it out in coordinates, realize is a fully decoupled system, and everything just falls into place, and pretty much, short version, pretty much the answer is eigenvalues and eigenvectors. I mean, assemble them, according to a certain formula, but details, the big picture, that everything works out great. Not such a happy story in the non-diagonalizable case. Right? So let me remind you what we saw last time. Non-diagonalizability means that you can Jordanize, thus resulting in what you might call a Jordanized system, which it's just not decoupled. It just isn't, right? That's too bad. But even though it's not decoupled, it is close to decoupled, right? You look at these three equations here, and that last equation is decoupled. Once you find that solution, then you know everything that you need to know to solve that equation. I mean, it's tedious, but you can totally do it. And once you know that, then you know everything you need to know to solve that equation. And then it's just a matter of assembling things and writing them in different form. And of course, don't forget that this only gives you the z's, right? All of this down here tells you the z's. And to solve for the y that you actually wanted in the first place, y is pz. Okay. So we saw a bunch of details with this last time. Here's just a quick passing glimpse at, wow, look at all, that's a lot of details. Right? So do make sure that you're good at the execution, the proficient execution of these details. From Chapter 4, right? You recognize a lot of Chapter 4 stuff in here, because ultimately that's what this all boils down to. Okay, moving along. Here's the next thing we talked about. We talked about this special case of 2x2 matrices. And I know we talked about this last time, but I want to give you just a kind of a slightly different point of view on it here. The point of view I'm going to take here is, well, for one thing, there is only one Jordan form, so when I say 2x2 non-diagonalizable, I'm talking about that, fundamentally. As the Jordan form, of course, it's not going to look exactly like that. The original matrix is going to be something different, but this will be the Jordan form. So this is really all what we need to focus on. So, problem, the basis that you use here, that basis consists of, one eigenvector because of that first column being nice, right? And then how do I find this second eigenvector? I don't know, right? That's, again, regretfully, we just don't have in Math 216 a way of doing that we can reasonably talk about in the time that we have. So what do you do about that? Well, the assertion that I made is that you take that one eigenvector that you can find, because, that's Chapter 5, you know how to find eigenvectors. Take that one eigenvector, use that, sure, right? And this second Jordan basis vector that you can't find, don't worry about it. Just forget about it entirely. Just pick any other vector that makes a basis. So anything that's not a multiple of V1. Any other vector, and you're good. Let me try to argue now why it is that you're good. This is the new perspective that I want to give you. This first column here. That first column, with respect to this basis, tells you that equation. It says AV1 is equal to lambda V1 plus 0 V2. Right, there's those coefficients, lambda and 0. The basis V1 and V2 are what you're taking a linear combination of. So this first equation says that. Okay, my assertion is that if you use this other basis now, if you use this basis, wrong color. Use this basis, then you get this as the first column, lambda and 0. And how do I know you get that? Well, because in the same way that this column here tells me that equation, this column here tells me a very similar looking equation. Look at the coefficients, lambda and 0, but we have a new basis now, so now it's V1 and W, so the equation becomes 0W. And who cares? Right? I mean, who cares if it's 0V2 that we're adding in or 0W that we're adding in? Whatever, it's still 0. Right? So another way to say it then is that ignore this non-existent second term. That equation, that one equation, the fact that V1 is an eigenvector, which you get from that part of the Jordan form, that alone is enough to tell you that you're going to have lambda 0 in your first column of your new matrix. And what we really care about, as we've discussed before, what we really care about is that 0 right there. That's what makes this back solvable. And it's not in Jordan form, or at least, generically it won't be in Jordan form. Yeah, you might get lucky. You never know, right? But generically it'll be some other number up here, but who cares? The only reason we need a Jordan form in the first place, at least as of the moment, is because there's a 0 down here below the diagonal, all zeros below the diagonal. That makes it back solvable, and now off you go. And so, for example, we went through this example last time, so I won't go through the details again. But for this matrix, we have one eigenvector. I picked the wrong color. Look at that. We have one eigenvector, easy to find. Y'all know how to find eigenvectors. Pick that vector. And then pick, I really don't care, whatever vector you like here for this second vector. It was pointed out to me, by the way, in office hours, somebody asked the question, wouldn't it make sense to just use the easiest vector you could possibly think of there? And yeah, I think that's a good idea. If it doesn't matter, right? Yeah, I mean, don't pick a multiple of the first vector, but if it doesn't matter, pick the simplest vector you can think of. 1, 0 comes to mind as a reasonable choice. 0, 1, whatever. Zeros being nice numbers. Okay. All right. Making that choice for a basis using the eigenvector, as we just discussed. Use that basis. Do the change of basis. And our matrix with respect to that new basis, our matrix becomes back solvable. And there's a bunch of details of how do you got to solve that second equation, and then once you solve that second equation, that tells you what you put here, which then gives you a non-homogeneous first equation, and you got to play the game, write down the characteristic polynomial, all that jazz, right? But doable. How are we doing? Is everybody on board? Any questions? Okay. All right. All righty. Okay, so let me show you another way to do these now, or in some cases. So I am going to make a definition that we have not previously made. The definition is going to seemingly be a little bit outrageous to start. I'm going to define what it'll mean going forward to raise e to the power of a matrix, which seems really wrong, doesn't it? Right? E to a power. E is a real number. When you raise a real number to a power, that's supposed to mean that you're taking that real number and kind of, roughly speaking, multiplying it by itself that many times. That's the way we've always thought of raising a number to a power. So how do I multiply e times itself a matrix number of times? That makes no sense at all, right? Okay. I'm going to make the definition of this doubtable expression as being this Taylor series. Y'all recognize the Taylor series for the exponential function. And this actually gives me a pretty good callback to justify why this is not unreasonable. And that is, we have already made a definition in this class of how to raise e to the power of something that at first thought seems completely unreasonable to raise e to the power of. And that is an imaginary number. right? So what is it? How do you multiply E times itself? I times. Right? It doesn't fit our pattern. But you write down Taylor series. Whatever you have up here, when we were talking about imaginary numbers, you can, if you had an imaginary number here, note all you have to be able to do to make sense out of this expression is to be able to multiply that exponent by itself some number of times. I need to be able to multiply by scalars, those being these Taylor coefficients, and I need to be able to add these results. That's it. Anything you can do that with, you can raise e to that power. I can do it with imaginary numbers, and I can do it with matrices. Yeah? What do you think? Weird? Willing to buy it? Okay. All right. Why do we define weird algebraic objects? Because once you've defined algebraic objects, you can talk about different algebraic properties that they hold, right? After we wrote down the definition of e to the power of an imaginary number, we started writing down properties of complex algebra, complex arithmetic. And we could then use those algebraic properties to actually do constructive things, as we did back in chapter 4. So we're going to do the same thing here. I need to write down some algebra of matrix exponentials. And I don't want to get into the weeds on matrix exponential algebra. It's a lot to say. Again, we just don't have time. So I'm gonna show you the highlights, the parts of this that are the most important. One is as follows: if you raise e to the power of this matrix, x times a, where a is constant. A is going to end up being the coefficient matrix in a system that we're interested in, if you're wondering where this is all going. X is our variable. So a being a constant, x being a variable, this expression, e to the power of xa, is a function of x, and I can talk about what it would mean to take a derivative of it. Right? And I can actually compute that derivative too. Here's how you compute that derivative. First observe that we have here matrix exponential. So just, plugging in straight from this definition. That's the definition of that matrix exponential. We take a derivative to see what happens. Take a derivative of both sides. This derivative applies pretty easily. The derivative of a constant is certainly 0. What's the derivative here? Well, there's a constant times x. Sure, the constant's a matrix, right? But if you think about what's in this product here is a constant matrix A, and then I've stuck an extra factor of x in every element of the original matrix A. When you take a derivative of each individual element, you're just, as usual, just losing a factor of x. So the derivative of xa, pretty easy to persuade yourself, just a. Okay? Continuing, what we have here is a constant, a squared over 2 factorial, times x squared. So again, a constant matrix times x squared. The derivative acts on each of those individual factors of x squared, and each x squared turns into a 2x. And so that turns into that. Et cetera, on down the line. Now, okay, what do you do with this? The clever move here is to realize that if you pull out a common factor of a from each one of these terms, notice that what is left over is exactly our matrix exponential e to the xa. And leaving the factored out a, we have our result. And here's the really good news. Now, admittedly, we have a brand new algebraic object here. When you have brand new algebraic objects, you can't just assume that the algebra is going to work out, symbolically the way you're kind of accustomed to. But in this case, it kind of did. All right, look at the result there. Y'all remember way back when, your Calc 1, that when you take the derivative of e to the power of x times a constant, okay, sure, it was a scalar constant back then, but that constant just factors out, or, pops down there like that, and that's exactly what happened here. Right? So if you were to just before we did this calculation, if you had just made a uncomfortably naive, wild guess of what this derivative would have been, probably would have guessed this. Okay. All right. Who cares? We're making stuff up and proving properties about things that we made up and have yet to see why we should care about. Okay. Here's where we care about it. Remember, we're trying to solve differential equations. To be, more aggressive, we're really trying to solve initial value problems. I mean, wouldn't that be great if I could not only find every solution to this differential equation, but if I could further break it down by and with initial conditions, here are the specific initial value problem solutions. Wouldn't it be great if we could do that? Inadvertently, we already have. It's so weird, but check it out. You take this function here, that function, when you take its derivative, you get a times itself. That's what we proved up here. The derivative we saw previously, I'll do it like this. The derivative kicks out an extra factor of a. This derivative kicks out an extra factor of a. So this works. And we're kind of done, sort of, in a way, right? These are the solutions to the differential equation. In fact, we can further notice, not only do these functions solve the differential equation, these functions also satisfy the initial condition. Let's look at this initial condition. What happens to this function when I plug in x equals 0? If I plug in x equals 0 into there, notice I am raising then e to the power of, 0 times a. I'm raising e to the power of the 0 matrix. What is e to the power of the 0 matrix? Just plug into this formula here, e to the power of the 0 matrix. This simplifies very nicely as it's just the identity matrix. All the other terms go away. So, again, kind of familiar. We remember from high school algebra, e to the 0 is 1. Well, in matrix exponential algebra, e to the 0 matrix is the if you will, the 1 matrix. So, because of that works because this is just the identity. Anybody see what's going on here? Let me pause for questions. Okay. All right. So these are the solutions. Now there is something. Let me stop the sales pitch and let me get down to but what's the bad news? The bad news is that even though I have a formula here for every solution to every initial value problem, every homogeneous, of course. The bad news is I don't know how to evaluate this thing. Right? The only thing that I know about how to evaluate a matrix exponential is this infinite series, and I don't realistically want to have to add up all infinitely many of these terms, each of which involves raising a matrix to a high power, which is not always doable, especially if it's not diagonalizable, which it isn't. Right? So right now what we have is an abstract, kind of useless, practically speaking, answer. So that's the bad news. Okay, so what we got to do is we got to figure out how to evaluate this matrix. More to the point, we need to figure out how to multiply this matrix times vectors. Well, now here's a refinement of that statement. What we really need is we really wanted to find a fundamental set of solutions. That's what we're really hoping for. I mean, we know that, there's infinitely many solutions, but the way we understand infinitely many things in this context is to realize they have a linear algebra structure. They are a vector space. Understand that vector space by way of a basis for that vector space, namely a fundamental set of solutions. That's what this is, right? And so really what I want to do is figure out how to multiply this matrix exponential times, well, just a basis worth of vectors. I don't really need to multiply matrix exponentials times every possible vector. If I can do it for just enough vectors, then I've got a fundamental set of solutions. That's all I really need. Everything else is linear combinations. Everybody follow that so far? Now I'm leaving a detail for y'all to prove on your own. This would be a nice exercise. I want everyone to take a whack at this. Show that if you have a basis for Rn, show that as this theorem claims, that this is a fundamental set of solutions to the differential equation. Now, dimension argument handles most of this. I have n functions. This has an n-dimensional set of solutions, right? So everything lines up. All you really have to do is show that this list is independent. We have a list of vector-valued functions that you want to show is independent, and the way you're going to do that, details for you guys, is you're going to compute the Wronskian. You're going to take these things here, compute the Wronskian. In fact, you're just going to compute the Wronskian at a single value of x. You're going to compute the Wronskian when x is equal to 0. And, of course, we know that the Wronskian is either always 0 or never 0. So you're going to compute the Wronskian when x equals 0. You're going to show that it's not 0, and therefore conclude that this list is a fundamental set of solutions. So, details for y'all. Give it a try. As usual, feel free to ask if you have trouble. It's a nice exercise. Okay. So, how are we going to use this theorem? Specifically, what we have to decide is what basis do we want to pick? And here's where you get to make some choices. You can use any basis you want. Suit yourself. But we want to choose carefully, right? We've already recognized that we have this very nasty problem in front of us of whatever vectors we choose, we're going to have to figure out what the matrix exponential does to them. And we don't know how to write other than an infinite series. Practically speaking, we don't know how to actually evaluate this matrix exponential. Okay, so that's a problem. We want to make a clever choice of what v vectors to use. We want to choose v vectors that make it as easy as possible to evaluate these matrix exponentials. So here's the next observation to make. I'm skipping loads of algebra in order to get down to this theorem here. This is what I'm going to call. This is a result of boring algebra that's just got a lot of tedium in it, and it's not something that it's a good investment of our time. So I'm just going to assert this. You're welcome to take this as a free result. It's not that bad. If you really want to see it, come to my office hours. I'll be happy to work it out for you. It's not that big a deal. But this is a formula for how to evaluate matrix exponential times a vector. Now, why do we care? The reason we care about this formula... let me first trash this formula. Let me tell you what stinks about this formula. This matrix exponential is an infinite series. Right? So rather than multiply this infinite series times v, I can instead multiply this infinite series times v. So why does that buy me anything? Well, the answer is that you'll notice here this matrix shows up. That's the matrix that we keep raising to higher and higher powers. In that matrix, we have a lot of information about what that matrix does to particular vectors. Right? This matrix, A minus lambda I, is special. Yeah, of course, one thing you recognize immediately is this matrix is the matrix that you look at when you're studying eigenvectors. Right? Eigenvectors, for example. What happens if V is an eigenvector? If V is an eigenvector, A minus lambda I times V is 0. So this term times v disappears in a puff of smoke. This term times v disappears in a puff of smoke. All the remaining infinitely many terms in this series, when you multiply by v, disappear in a puff of smoke. Right? So for eigenvectors, this is kind of awesome. For an eigenvector, you just get e to the lambda x times the identity matrix times the eigenvector. In other words, you get just e to the lambda x times the eigenvector. Right, so this equation has already done a great service for us. This matrix exponential, when you multiply it by eigenvectors, this is a highly computable formula. Good old scalar exponentials, no problem, right? Times those vectors. Okay, going to pause for a moment for questions. Anybody? Okay, all right. Okay, so keep in mind, why are we doing all of this? We're trying to find a basis. Pick a basis, any basis, to multiply by the matrix exponential. We just found that if you pick eigenvectors, that matrix exponential product is easy to compute. So, upshot here, pick all the eigenvectors you possibly can, for sure. I mean, no doubt about it. Every eigenvector you have, for sure, that's in your list. That's something you choose. Everybody on board with that? Okay, so what do you do with what's your remaining choices? I'm going to motivate this, the last bit. What do you choose for your remaining vectors by asking, well, how did this work out so nicely? What was, in the big scheme of things, the tool, the fact that made this computation doable? Well, it was the fact that a minus lambda I has nice properties in relation to the eigenvector. So let's ask, what other vectors can we think of that fit nicely with a minus lambda I? And it turns out, it's just a matter of writing it down. There's some details we have to go through. But it turns out that Jordan basis vectors are going to fit very nicely with that requirement. And so let me remind you what we know about Jordan basis and Jordan form. Here's our Jordan form. Right? I want to look at a single block. Here's a single Jordan block. Inside of that Jordan form. Okay. Keep in mind the columns are telling you about the images of certain basis vectors. Now these are just the basis vectors that correspond to the columns that correspond to that block. Right? So not the whole list of Jordan bases, just the ones that sort of, like I say, correspond to columns that correspond to that Jordan block. Okay. And we know that's what that Jordan block looks like. And let me further remind you that we know how to interpret the meaning of these columns. Let's look at these a few at a time. Let's look at this first one here. That first column is telling me about T of W1, and it's telling me this. It's telling me T of W1 is lambda V1. Section 5.3, right? Columns give you coefficients of images with respect to the appropriate basis. Which means that in S language, and which I could rewrite as that. So you could take it as that first column is telling us what a minus lambda I does to that first Jordan basis vector. Reminder, we kind of already knew this. We knew that first Jordan basis vector was an eigenvector. And we already knew that eigenvectors are in the null space of a minus lambda I. So this is a reproduction of old news. But look what happens when we apply that same reasoning to the other columns. Let's look at these columns. All of those remaining columns corresponding to that block. They tell us about the images of the other Jordan basis vectors. Right? columns give you coefficients of images with respect to, of course, the appropriate basis, here the Jordan basis. So we get that, which, with respect to the standard basis, is that. And then if I pull this little trick, same trick where I take the lambda and move it over to the other side of the equation. Here I'm going to take this term with a lambda in it, multiply it, or switch it over to the other side of the equation. I get this. How we doing? Everybody on board? And look what we got. We got just what we wanted. We now have a simple formula that tells us what A minus lambda I does to Jordan basis vectors. That was on our wish list, right? Look back up here. We wanted to know, what does A minus lambda I do to Jordan basis vectors, so that we could evaluate matrix exponentials, so we could fill out our fundamental set of solutions. A minus lambda I, Jordan basis vector, and here's the answer. How we doing? Okay. Just to summarize, that yellow equation, if I were to put the Jordan basis vectors in order here, W1 through WK, this first result that we have tells us this. It tells us that A minus lambda I sends W1 to 0. The rest of these columns, the rest of these equations tell us this. A minus lambda I sends each Jordan basis vector to the previous Jordan basis vector. Nice and crisp, simple answer. A minus lambda I sends Jordan basis vector to the previous one. And that's why I have these little arrows moving to the left here. We had put down a list of all the Jordan basis vectors. A minus lambda I just sends you sort of backwards through that list until you get to the eigenvector. And of course, once you get to the eigenvector, the next A minus lambda I sends it to 0. Okay, so we have all the tools that we need now to deal with the matrix exponential formula. Keep in mind where we're at. We're trying to evaluate this great big monstrosity with an infinite series in it. Let's do that now with this result in mind. All of this in mind. Let's see if this will all fit. Oh, not quite. That is a shame. Okay, oh well. No, I didn't quite right. Okay, oh well. Okay. Jordan basis vectors go to previous Jordan basis vectors. Here's our formula, our original formula. Right there. Let's play the game. What happens to, if I put a Jordan basis vector here, Wi, what do you get? This is Wi. This is Wi. And let's take this one term at a time. What happens? Well, obviously the factor e to the lambda x stays there. What happens when I multiply the identity times Wi? Well, I get Wi. That's clear. Okay. What happens when I multiply A minus lambda I times Wi? Let's cheat. We'll go back up here to our list. According to this formula, or if you prefer, according to this little chart, this little diagram, A minus lambda I sends any given Jordan basis vector to, well, the previous Jordan basis vector in the list. So, okay, following that rule, A minus lambda I sends Wi to W sub I minus 1. Just the previous vector in the list. Okay. The x, of course, comes along for the ride. Okay, what does A minus lambda I squared do to Wi? Oh, well, A minus lambda I squared. What that means is I'm going to start with Wi. I'm going to multiply by A minus lambda I, and then I'm going to multiply by another A minus lambda I. Okay? So I am therefore going to go to the previous Jordan basis vector in the list, followed by then going to the one previous to that. So, said differently, I'm going to go back to 2 previous. And so, W sub I minus 2. Et cetera, et cetera. This just keeps right on going until, of course, eventually, there's the first one that you do, and then the second one goes to 2 previous, and then the third one goes to 3 previous and 4 previous, etc. Eventually, you get back to W1. That's the eigenvector, right? What about the term after that? Well, the term after that's going to multiply that times A minus lambda I, and that then gives you 0. And every higher factor of A minus lambda I still gives you 0. So once you get to the eigenvector, you stop. Once you get to the eigenvector, so notice in this list, once I get to the eigenvector, I've stopped. And we have here then our formula for what matrix exponentials do to Jordan basis vectors. And this is going to be crazy, crazy powerful for us. We'll see an example just momentarily. Matrix exponential times Jordan basis vector, e to the lambda x. Write down that Jordan basis vector. And then one term after another, just keep going through this series where the coefficients are doing sort of an exponential Taylor series thing, you'll recognize. And the vectors that you're multiplying by are just continuing one term at a time to go backwards through the list of Jordan basis vectors for that block until you get to the eigenvector, and then you stop. Everybody see the pattern? Okay. All right. Okay. Let's see how this works out. Here's a differential equation. I hope you all might recognize this differential equation. We looked at this last time, I guess it was, and we used this in a failed attempt to decouple. Right? It didn't decouple because this isn't diagonal form, but it at least gave us a foot in the door. And here's that sort of this third row down here gives us one decoupled equation, and then we did that whole back solving thing. Right? And once we back solved, we had to multiply by the P matrix. This was our P matrix, and it was a whole thing. It took like 3 pages of algebra. Yeah, everybody remember all that work? Let's use our new trick. Let's use our matrix exponentials and Jordan basis trick and see how this plays out. So first of all, just a reminder, this is, let's see here, to be clear, this is TSS. This is TVV. Therefore, this has got to be the one that's change of basis from V to S. Therefore, our Jordan basis are the columns of that left matrix, and therefore that's our Jordan basis, right? Make sure to think it through, again, don't memorize, it's always the one on the left, or it's always the one on the right, or it's if A is on the right, then it's, that's not going to work, right? So think it through, be clear, where do you find your Jordan basis vectors? These are they. And with that done, it's just a matter of plugging in now these Jordan basis vectors into this formula and writing down our solutions. Okay, here we go. We'll take these one at a time. I'm going to have to zoom out. Okay, one at a time. Let's start with this first Jordan basis vector, W1. That first Jordan basis vector, W1, I'm going to plug that in here, right? If that's W1, then that's W1. Oh, which by the way is an eigenvector, and therefore we stop. And so the matrix exponential, this first solution that we're looking at is e to the lambda x times W1, like so. All right, everybody good with the first one? Okay. Okay, now, next. Next, let's look at this second Jordan basis vector that we're going to plug in right there. Right? Again, I need to multiply by this matrix exponential, like so. So I got to do that. Got to do all of this stuff. Now, this here, this Jordan basis vector is W2. So this is W2 right there. That makes this W2 right there. That makes this W1 right there. And that's the eigenvector, and we stop. And so we get that. Everybody see what happened there? This is how this plays out. Okay. All right, next one. Let's look at our W3. We're going to multiply that times the matrix exponential to get our third solution. That we're going to plug into this formula by, well, notice that now we're looking at this as W3. That makes this a 3. That makes this a 2. That makes this a 1, and thus the eigenvector, and I stop. Whoops. And then that's that. Everybody see the pattern? It's always the same pattern. That's the nice thing. Those coefficient functions are always the exponential Taylor coefficients. So 1x, x squared over 2, x cubed over 3 factorial, et cetera, et cetera. It's always the same coefficients. It's always the same pattern on the vectors. You're always moving backwards through the list of Jordan basis vectors. You always stop when you get to the eigenvector because, of course, that's what this pattern here says. You stop when you get to the eigenvector. Right? So it's always the same pattern. Okay. Now, is this helpful to us? Does this bias anything? I mean, how much does this actually? Is this a win for us? Well, look how easy it is now to plug in and see the actual solutions. We know what the Jordan basis vectors were. We saw previously that this first Jordan basis vector was 1, 0, 1. All right, you can see the 1, 0, 1 multiplied by x there. You can see the 1, 0, 1 being multiplied by 1/2 x squared there. Right. Likewise, for the second Jordan basis vector, 4, 2, 3, you can see it right there. You can see it being multiplied by x there. And likewise, you can see the third Jordan basis vector there. And so there's your fundamental set of solutions. Now, just for comparison purposes, I mean, which do you like better? Do you like this argument here? Let's take stock. How much work did it take us to do this? It took us 2/3 of a page here using the matrix exponentials, as compared to, before we looked at matrix exponentials, it took us kind of 2.5 pages, right? We saw that we can do this change of basis, right, to sort of almost decouple, and then you had all this back solvings to all this sort of tedious, easy to get lost in the details of Chapter 4 differential equations. And then you write that, and then you write the corresponding fundamental set, and then you multiply by the P matrix. It was a whole thing, right? It was 2.5, easily 2.5 pages. None of that back solving is necessary if you use this matrix exponential trick. How are we doing? Everybody happy? Yes?
On the exam, are you going to ask us to solve it a specific method, or does you have a choice?
Maybe. Sometimes it depends on the role that question is playing in the exam. So, it's not always the case. As I'm sure you recall, this course is more so about ideas than answers. And so sometimes I want to see, do you have proficiency in a specific method? On the other hand, sometimes I might want to not tell you the method. I want to see, can you identify a good method? And so either, depending on the circumstance, I either will or won't give you the flexibility. But I'll always make that clear in the statement of the question. Yeah. No. Right. Anybody else? I will say this also. One drawback to this matrix exponential method is this matrix exponential it's kind of concealing the importance of the change of basis. Right? You could take this as, hey, if you know the Jordan basis, if Maple has spat out the Jordan basis for you, then plug into this formula and we're done. Right? So it is true though that this process here, this change of basis process, is important in other contexts other than solving specifically these differential equations. So certainly it is not good enough to say, phooey on this, I'll never do this ever again in my life. I'm always going to use the matrix exponential method. You can't do that. It's very important to understand both methods. Yeah. Okay. Alrighty. Okay, so a couple of last things that I want to say about the matrix exponential method. Let me go back to this page. Remember, this whole page. Whoops, wrong way. Here we go. This whole page, this diagram, what does A minus lambda I do to Jordan basis vectors? Well, it depends. Are you talking about not the first Jordan basis vector for a given block? Or are you talking about the first Jordan basis vector for a given Jordan block? The big difference, of course, is that the first one always an eigenvector. The others, never eigenvectors. Right? So you get these different equations accordingly. Said differently, and it's all about, you can look at the block here. The block has a first column, and it has a bunch of not first columns. Right? Those not first columns are the ones that have the ones in them, which is what makes them get treated differently. Okay, so the big point I'm trying to get to is, don't forget that as you're moving backwards through this list of Jordan basis vectors, when you get to the eigenvector, you stop. You have to stop there because, well, that's what A minus lambda I does. A minus lambda I turns all the rest of those terms into zeros. It stops, right? It's not arbitrary. It has to. Okay. So, when, for example, you have an example, let's look at this example right here, where there are multiple blocks. Here's our first Jordan block. Here's our second Jordan block. There's our third Jordan block. Right? Compare our first example that we saw. There was just the one Jordan block. We didn't have to worry about this. When there are multiple Jordan blocks, each Jordan block, per our setup, corresponds to certain Jordan basis vectors, which give you a corresponding little diagram. And then likewise for the other blocks, right? This second block corresponds to this second group of Jordan basis vectors, which then gives you this second diagram. And notice, sure, V4 goes to V3. You would think that V3 goes to V2, but it doesn't. V4 goes to V3. V3 goes to 0, because that's the end of a block, right? You stop when you get to the eigenvector. You don't proceed into the next block. Okay, so you can see that in how the equations work out, how these solutions work out. These solutions come from these vectors, and this diagram, these solutions come from these vectors and this diagram, and notice that in both cases when you get to V3, you stop at V3. You don't go on to V2 or V1 in evaluating these down here. Does everybody see what I'm talking about? This is an important. A lot of students mess up on this and just think, oh, you just keep going backwards through the list. It's separate lists for each Jordan block, and you never move from one to the other. Lastly, then, of course, notice that this last Jordan block corresponds to just the vector V5. It has a really boring little diagram, and you get just the one term. Of course, it is an eigenvector, so that one's an easy one. All right, out of time. See y'all later. Have a good Wednesday.